First of all, Pixy2 can be connected through the following interfaces: serial communication, including SPI, I2C, and UART, as well as USB. Additionally, although there are limitations in functionality, it is also possible to communicate with Pixy2 using analog digital communication. First, looking at the characteristics of each interface, in the case of USB, it is generally assumed that communication occurs in an environment where the operating system is running. In that state, we need to use the Pixy2 related USB libraries, just like we did when using Raspberry Pi or BeagleBone Black. So, we use the libsusb2 library for communication, and currently, it is the fastest among the interfaces mentioned earlier. So, if you want to use the PC tool at the highest speed, it's best to use USB. The next fastest option is SPI, which is used for communication between Pixy2 and Arduino. It communicates at a speed of 2 MHz, making it faster than I2C or UART. And if you want to use Pixy2 with a different microcontroller instead of Arduino, and you want to communicate at high speed without using USB, it is better to use SPI. Next, there is communication via UART or I2C, and in this case, when looking at UART, you can set speeds ranging from 19,200 bps to 12,500 bps. However, since I2C is more flexible for connections, it is preferable to use I2C whenever possible. That said, since the speeds of UART and I2C are the same, you can choose based on your specific situation. To set up the interface, click on the gear icon in our Piximon, and you will see the Interface tab. Here, in the document, there is a specific section that explicitly mentions the data output process. Here we have Arduino, ICSP, SPI with slave select pin, I2C, UART, analog digital X, analog digital Y, and Lego I2C. I won't explain Lego here. This is related to Lego, so I will skip the explanation. When we explained Pixy, there was a pin header at the back. And if you look here, there is a UART RX pin, and this is the SPI pin. It serves the role of master in and slave out pins. Next, there is a pin that can function as a 5-volt input or output. Pin 3 is the SPI clock pin. Here is the SCK pin, and pin 4 is the SPI master out. Slave in pin for UART, there is the TX pin, and pin 5 is the clock pin for I2C, known as the SCL pin. Pin 6 is ground, pin 7 is the SPI slave select pin, pin 8 is analog out, pin 9 is the data pin for I2C, known as SDA, and pin 10 is VIN, which can actually receive power from 6 to 10 volts. You don't really need to pay attention to this part. It doesn't matter about the interface right now, at that time. These are the pins related to the servo motor when we control the motor kit. If you set up the Arduino using the Serial Peripheral Interface SPI protocol, excluding the power connections and assuming only the data pins are considered, you will need to use a total of 3 specific pins. Pins 1, 3, and 4, which are essential for the communication process. When communicating via SPI, a slave select pin is used. We do not use a slave select pin. And when we connected it to the Arduino at that time, the connector pins fit perfectly. So if you just plug that connector directly into the ICSP connector on the Arduino, it will connect immediately. Next, we have SPI with slave select. Although slave select was not used before, it will be used here. If you want to control the enable or disable functions related to the slave select pin when communicating with other SPIs later, you can set it in this mode. When using this mode, you need to control the enable and disable functions through the slave select pin. I'm sorry, but there are 4 pins, not 3. We use pins 1, 3, 4, and 7. Next, when using I2C, you only need 2 pins, SDA and SCL, which are the data and clock pins, using pins 5 and 9. You can set the address, everyone. So, if you set the address, you can configure up to 127 addresses. Now, if the I2C address is fixed for PC2, you would only be able to connect one PC tool. However, since you can set the address here, if you connect to a specific microcontroller via I2C, you can connect up to 127 PC tools using this address setting. Next, the UART interface obviously requires 2 pins, TX and RX, which are pins 1 and 4. You can set the baud rate. You can do this by adjusting the UART baud rate settings in the configuration window to set your desired BPS. There are analog digital X and analog digital Y, providing the X and Y coordinates of the center of the largest object recognized by PC2. Unfortunately, the downside is that, as you can see here, there is only one analog output pin for pin 8, which means you can only monitor one X coordinate and one Y coordinate. And now, we use pin 1 and pin 2. As mentioned earlier, pin 8 is for analog output, but we use pin 1 to determine whether recognition was successful or failed. And here the voltage range is set from 0 to 3.3 V. This voltage value is received as an analog input, and with this magnitude we can check the size of the coordinates. The same applies to Y. So, as I mentioned regarding the analog input, there is only one analog output pin, which means you have to choose either X or Y because of this. You can select this in the settings, and as I mentioned, it provides the center, X coordinate and Y coordinate of the largest object recognized by PC2. So, if pin 1 is high, it is recognized, and if pin 1 is low, it is unrecognized, which means there is no need to check the analog output. Assuming it is recognized, if the voltage is 0 V, then X is at the far left. If it is 3.3 V, then X is at the far right. Next, if it is 0 V, then Y is at the bottom. And if it is 3.3 V, then Y is at the top. In the case of serial protocols like SPI, I2C, and UART, the communication methods differ, but the protocols are all the same. If you take a look at the packet structure, you will see that, generally, the request includes 2 fixed headers at the front. The response also includes 2 headers, but they are slightly different. Here, the hex value, AE, is included, and the response contains AF. Next, the type values are included, which consist of the request type and the response type, as well as the data length. There can be cases where the data length is 0, or it may be non-zero when making a request. So, I will explain this when I discuss the protocol next time. In the response power section, if you look at the data length, the next 2 bytes are the checksum. This checksum is represented as a 16-bit value that is the sum of all the data bytes that follow. For example, the first byte is the checksum first, and the second byte is the checksum second. For example, let's look at a version request. In the case of a version request, the first byte is a hex value, and here are all hex values, A2, C1. Next, the version request type is 14, which is 2 in hexadecimal when converted to decimal, and since the data length is 0, there is no separate data. Then, when the response comes in, it arrives like this. So, it's AFC1, and the response type is 15, which is F in hexadecimal. The data length is 16, which is 10 in hexadecimal. After that, since we don't know what the data will be, the checksum will come in as a 16-bit value that combines all this data. You should check this to ensure there are no issues with the checksum. If everything is fine, you can proceed with data parsing. The first 2 bytes represent the hardware version, the next 2 bytes represent the firmware version, the following 2 bytes represent the firmware build number, and the subsequent ones contain firmware information in ASCII format. You can convert these directly into a string. You can understand that the protocol is structured this way. Next time, I will explain the protocol in detail. This time I explained how to communicate with Pixy2 using various interfaces. In the next session, I will explain in detail how communication works using serial protocols among them. Then I will see you next time.